Let us try to understand what will be the extension or shortening of a bar. And to understand this, first let us try to understand what is bar. Now, bar is a 1D structure member. Bar is a 1D structure member. Alright. Now, why we call it as 1D structure member? Because in case of bar, what happens is that one of its dimension is usually very large compared to its other two dimension, and that is why we call it as a 1D structure, because one of its dimension is very large compared to the other two dimension. Consider this, take this example of off-road vehicle, and then this is the roll cage. This structure which you can see here is the roll cage, whose analysis has been performed here. Now, if you consider an individual member of this structure of this roll cage, you can see that its length is very large compared to its cross section, and therefore we can analyze it using the approach of 1D. So basically, bar is nothing but it is a 1D structure member whose dimension is very large compared to its, whose one of the dimension is very large compared to its other two dimension. So usually in case of bar, which dimension is very large compared to other two dimension? Its length, right? Its length. Its length is very large. Its length is very large compared to other two dimension, that is its cross section. Yes. So therefore we call it as a bar. I mean we call this bar as a 1D structural member. All right. So let us see what is extension or shortening of bar. Now, in this case, we have this bar which is subjected to, say, axial force P, right? Since it is subjected to axial force P, the bar which was of original length L will undergo deformation and it will elongate. So basically what will happen in this case, the extension will take place in this case, right? So since the original length was L, the change in length or the extra length which will which this bar will gain is dl. Let that extra length which it gains be dl after we pull it in its axial direction. Then in that case we know that the stresses that will be developed in this bar can be given as sigma is equal to P by A, right? So what is A? A is the cross sectional area. Suppose say if the cross sectional area of the bar of this bar is say a rectangular cross section, then this cross section, this will be its, this will be its cross sectional area, right? This will be its cross sectional area. All right. So stresses in this cross sectional area can be given as P by A. Now similarly, what, how do we define strain? As we had seen last time, strain can be given as change in length by original length. So so this will be change in length, this will be original length. So strains can be given by change in length by original length. And with the help of Hooke's law, we know that stresses are proportional to strain in elastic limit, under elastic limit. And let me again remind you, in this course we will be only dealing with the deformation when they are under elastic limit. So basically deformations are very small. So under elastic limit what happens is that stresses are proportional to strain, or under the limit of proportionality stresses are proportional to strain, and we know that from here we get sigma is equal to E times epsilon, where E is Young's modulus. Now suppose say if we combine these three equations, if suppose say this is our equation 1, this is our equation 2, this is our equation 3. If suppose say if we combine this all these three equations in order to find what is this change of length, then we can find it in following manner. See, from equation 2 we get what? From equation 2 we will get dl is what? Strain times original length L, right? So we'll get this dl as strain times original length L. But from equation 3 we know that strain is what? Stress divided by Young's modulus. So I can write this as stress divided by Young's modulus multiplied by L, right? But from equation 1 we know that stress is what? P by A. So in case of sigma I can further write this as P by A, and I have here L with me and I have here E with me. So basically this is the formula, dl is equal to PL by AE is the formula to calculate the deformation in a bar which is subjected to either tensile loading or compressive loading. Now Even in this case, in case of compressive loading also, what will happen is, since the original length was L, and since the compressive load are applied at the two ends of this bar, we will try to shorten this bar, right? Or we will try to compress this bar. So this is basically shortening of the bar. So basically for compressive loading, we will try to shorten this bar. And then if suppose the original length was L and the change in length is DL after applying this compressive load, then this change in length can be found out by the same formula. Alright. So basically this is the formula to calculate the extension or shortening of a bar, where what is P? P is the load which is applied on this bar. Truly speaking, P should have been the resisting load R, right? But we know that in this case this R, which is the resisting load which will be developed here, which this R will be same as this applied load P. So this DL formula, or this formula to calculate the extension or shortening of this bar, will work when P is known to us, original length is known to us, the cross sectional area should be constant throughout the length, this cross sectional area A will be constant throughout the length, and E is the Young's modulus or the property of the material. So once we know all these quantities, we can very easily find what is the deformation in this material, what is the extension in the material, or what is the change in length of the material. Now with the knowledge of this and then the previous concepts which we had done in our previous videos, what we will do is we will try to solve this problem. Alright, this is a very simple, very easy problem, but let us see how to solve it. So basically we have a specimen of steel of 20 mm diameter with a gauge length of 200 mm. So gauge length, we have one specimen here, we have one specimen whose gauge length, let us call this as a gauge length from this point to this point. So this gauge length is how much? This is given as 200 mm, right? This gauge length is given as 200 mm. And then the specimen of the steel, or what, how much is the diameter of this? The diameter of this specimen, the diameter of this specimen is how much? It is 20 mm. So this B is 20 mm. All right, is tested to destruction. So basically we'll be applying the axial forces on it, we'll be applying axial forces, and we'll be testing it for destruction, that is up to its rupture or up to its failure, we'll be loading it. Then it has an extension of 0.25 mm under the load of 80 kilonewton. So basically what it is saying, when this load reaches how much, when this, let me draw this bar again. So this, there will be some extension in this bar, there will be some extension in this bar. When the load applied reaches to how much, it reaches to 80 kilonewton. So basically it is 80 multiplied by 10 to the power 3 newton. When this is the case, then the change in length, then this change in length from here to here is how much? It is 0.25 mm, right? And then we are also given that, and the load at elastic limit is 102 kilonewton. So load at elastic limit, load at elastic limit is how much? It is given as 102 kilonewton, but it was said that it is tested for destruction. So how much is the load? So maximum load which is applied is 130. So this is the load at destruction. So P maximum or P destruction is how much? 130 kilonewton. So basically we need to find the stress, all these quantities, and then also it is given that the total extension as at fracture is 56 mm. So basically when this will get fractured, all right. So after fracture, basically after fracture, after all this, once the fracture takes place, the length becomes how much now? It original was 200, right? But after fracture it will become how much? 200 plus 56, 200 plus 56, which will be 256 mm. So this is the length at fracture, all right. So after this excessive load, of 130 kilonewton, the fracture will occur, and the length at the fracture will be how much? 56 mm. So length at the fracture is 56 mm. So at this stage the total length will be 256 mm. And how much will be the diameter? He has said that this diameter here will be how much? It will be only 15 mm. What was the original diameter? It was 20 mm original diameter, but after this excessive loading of 130 mm, the diameter will decrease, right? And the diameter which decreases is to 15 mm. So from 20 mm, the diameter goes to 15 mm. Alright, so with this information, we need to find all these quantities. So let us take these quantities one by one. So first thing what I need to find is, the stress at elastic limit. So basically we need to find the stress at elastic limit, the stress at elastic limit, right? So basically they have given us that the load at elastic limit is 102, right? The load at elastic limit is 102. So moment we have to find stress, we know that the formula to in order to calculate stress is what? P by A. But here our only question will be, since the stresses are asked to since they have asked us to calculate the stresses at elastic limit, then which load and which area? So basically this load has to be the elastic load, right? The load of elastic limit, and area will be our original area. So this will be 102 multiplied by 10 to the power 3 Newton, because this is the load at elastic limit, divided by our area is how much? Pi by 4 multiplied by d square. But how much is d? D is 20, so it will be 20 square, and this will be mm square, right? So further I can write this as 102 multiplied by 10 to the power 3 divided by this area will be 314.16. So basically this original area, let us just write this original area and keep it, because we will require it frequently later on to solve all this. So this will become 314.16 mm square. So I will get this stress at the elastic limit as 324.675 megapascals, right? I hope you all know why I have written here megapascals, because the units are Newton per mm square, and Newton per mm square can be written as megapascals. Newton per meter square is nothing but pascals, but the moment we have Newton per mm square, it becomes megapascals. So similarly we can find the second quantity now, that is Young's modulus. We also need to find Young's modulus, right? So Young's modulus. So basically Young's modulus is nothing but the moment someone asks us to calculate Young's modulus, the law which should come to our mind is Hooke's law, that is stress is proportional to strain within what? Within elastic limit. So this relation will work only within elastic limit in this region. So in this region basically sigma is equal to E times epsilon in this region, right? So therefore we will be able to find this E1, I mean this Young's modulus E, as sigma divided by epsilon. So what these quantities, all these quantities, stress or strain quantities, in order to calculate Young's modulus, should be within the elastic limit. So we cannot consider any values of stress or strain beyond this point to calculate the Young's modulus. Whatever quantities we will be taking, stress or strain quantities we will be taking to find Young's modulus, it should be within this elastic limit. So for that we know that sigma can be given as P by A, and the strains can be given as change in length by original length. Now which load to be considered and which this change in length to be considered, which original length and which area to be considered? As I told you, all these quantities has to be within the elastic limit, and for that we know that this 0.25 mm is the extension under a load of how much? Under a load of 80 kilonewton, and the elastic limit is at how much load? At up to 102 kilonewton, right? So up to 102 kilonewton, whenever we will be applying load up to 102 kilonewton, it will retain its elastic limit. So basically at when we apply a load of 80 kilonewton, it will have an extension of 0.25 mm. So we can very well use this 80 multiplied by 10 to the power 3, because it is given as 80 kilonewton divided by area. Now area will be this area, right? Area will be this original area. So that is 314.16 divided by how much is the change in length? Change in length is how much? For this load it is 0.25. So this will be 0.25 divided by how much is the original length? It is 200. So basically whatever quantities we have taken here, all are within the elastic limit, because the elastic limit is at 102 kilonewton. Suppose say if we had taken this as our change in length 56 mm at 130 kilonewton, can we take it to find this Young's modulus quantity? No. Why? Because this 56 mm fracture or extension at fracture will occur when the maximum load of 130 kilonewton is applied. But since 130 kilonewton exceeds this 102 kilonewton, this 130 kilonewton will be somewhere here and 102 is here. Since this load exceeds this load, therefore we cannot use these terms here to calculate Young's modulus. So we will have to calculate Young's modulus with all the quantities which are within the elastic limit. So if we substitute all these values now, I should get this E as 203.718 Newton per mm square, which will be 203.718 gigapascals. So now let us find the third quantity, that is percentage elongation. We know that the percentage elongation can be found as percentage elongation. The percentage elongation can be calculated as L dash, that is the final length or the length at fracture, minus the original length L divided by the original length L, and we have to multiply this by 100. This is how we can calculate the percentage elongation. So how much is the final length now at fracture? Final length at fracture is 200 plus 56, which is 256 mm, right? Minus original length. How much was the original length? It was 200. So this will be 200 divided by 200 multiplied by 100. So basically we will get this as 56 divided by 2, right? This will be cancelled out. 256 minus 200 is 56, and therefore the percentage elongation will be how much? This will be 28%. This was easy. Then fourth quantity. The fourth quantity which we need to find is percentage reduction in area. So percentage reduction in area can be calculated as original area minus the area at the fracture divided by original area, and this we have to multiply by 100. So basically this original area will be given as pi by 4 multiplied by d square minus, okay, first let us write this, multiplied by d square, original areas, minus now the area at the fracture. So when the fracture occurs, how we will calculate area? We will have to calculate area with this diameter d dash. Alright, so that is how much? It is 15, right? So this will be pi by 4 multiplied by d dash square, because this area will be at the fracture. That is how we calculate the percentage reduction in area, percentage reduction in area. So this, and we have to multiply this by 100 since it is percentage reduction. So I can very well cancel this pi by 4 term. So I will get this as d square minus d dash square divided by d square, and I have to multiply this by 100. So the original diameter was 20 minus the diameter at the fracture becomes how much? 15. So this will be 15 square divided by 20 square. I have to multiply this by 100, and I will get this value as 43.75%. So this is how we have calculated the fourth term which they had asked us, that is percentage reduction in area. And the fifth quantity which we need to find is ultimate tensile stress, right? We need to calculate ultimate tensile stress. So this is the maximum amount of stress which the material can withstand before it undergoes fracture or failure. So this can be calculated as, since this is stress, we know that it should be load by area. But now again, which load and which area? The load will be the ultimate load or the maximum load. This will be the ultimate load or maximum load. And how much is the ultimate load? How much is the ultimate load in this problem? We know that the ultimate load is how much? It is 130 kilonewton, right? So this will become 130 multiplied by 10 to the power 3 divided by area, and the area will be considered as the original area itself, because we will be finding all the stresses in terms of nominal stresses. So this will become 314.16. So this will become 314.16, and this shall be equal to 413.80 megapascals. So this is how we can calculate, or we can find different parameters. We have here one more problem, and this is more kind of a design problem. A hollow steel tube is to be used to carry a axial compressive load of 160 kilonewton. So basically I have here a hollow steel tube, right? We have here a hollow steel tube, and hollow meaning it is hollow from inside, it has some thickness, and then its function now here in this problem is to carry a compressive load of how much? It has to carry a compressive load, it has to carry a compressive load of 250 of 160 kilonewton. This is the compressive load which it has to withstand. The yield stress of this material is 250 Newton per mm square. So the yield stress sigma yield, that is the yield stress of this material, is given as 250 megapascals or 250 Newton per mm square. This should be mm square. So this is the yield stress of this material, and then he is asking us to consider a factor of safety, FOS, factor of safety of of how much? Of 1.75 in the design. We have to consider a factor of safety of 1.75 in the design. The following three class of tubes of external diameter 101.6 mm are available. Which section do you recommend? So basically this is a design problem. Our customer wants to use a hollow steel tube of external diameter of this external diameter, how much? 101.6 mm. And what is the function of this steel tube? To withstand the compressive load of 160 kilonewton, and its yield stress is how much? 250 Newton per mm square. It shouldn't exceed the 250 Newton per mm square. And basically he wants us to recommend which class of tube we should we should suggest. Now there are three classes of tubes. One is light, one is medium, one is heavy. What is the difference between these three classes? The thickness is basically varying. The lighter tube has a less thickness, and that is understood, right? As the tube will be lighter, the thickness will be less. This is of medium class, and this is the heavy class, wherein the thickness is the maximum. Now we just cannot blindly suggest him to consider this heavy tube. Now what will happen if we just blindly suggest him to consider this heavy tube? It may be over designed to withstand this 160 kilonewton. In that case, what will happen is he will have to spend more on this tube. He will have to, since the material will be more, since the thickness is more, material will be more, and it will become more expensive to buy this tube. And also we cannot just suggest randomly to use light or medium, because they might fail in this applied load. So we will have to have a proper design approach in order to suggest him which class or which kind of tube he will have to consider in order to satisfy all these criteria. So for this, what we will have to do is we'll have to we'll have to have a proper design approach in order to come up with proper solution. So first of all, since the yield stress for this material is given to be 250 and the factor of safety is 1.75, we'll have to find how much is the working stress which will get induced in this material. So we know that the factor of safety is nothing but the yield stress divided by working stress. So the working stress can be found out as working stress is equal to yield stress divided by factor of safety. So how much is the yield stress here? It is 250 divided by 1.75. So because of this, the working stress will come out to be 142.875 megapascals. So this is the working stress. So basically we can subject this to a maximum stress of how much? 142.875. Although the yield stress is 250, but since we are considering the factor of safety, we want to be on safer side of 1.75. Therefore the working stress or the maximum stress which we can allow in this material is 142.875. And then basically we need to find now this thickness, right? So this thickness can be found by area. So area, in order to find area, we know that stress is P by A. Stress is force divided by area. So here the stress, the maximum stress which we can allow is 142.875. How much is the maximum load which will be applied? It is 160 kilonewton. So let me write it in terms of newton. So therefore it will be 160 multiplied by 10 to the power 3 divided by area. Now how much is the area? This is exactly what we need to find. Now the area of this circle can be given as pi by 4 d square. But this is what? This is a hollow cylinder, right? This is a hollow cylinder or hollow tube. So this will be pi by 4 outer diameter square minus inner diameter square, right? Because this will be this area minus this area. So basically we are only interested in this area, the area which will resist this applied force, right? We are interested only in this area. This area is the area which will resist this applied force. So this area can be calculated as outer area minus inner area. So this will be pi by 4 outer diameter square minus the inner diameter square. So we know that the outer diameter of all these hollow tubes are how much? 101.6 mm. So basically I will have to substitute this as, this is equal to 160 multiplied by 10 to the power 3 divided by pi by 4. This is how much? This is 101.6 square minus d square. So basically we'll have to find from here what is small d. What should be the small d in order to withstand this load of 142 point, I mean in order to withstand this stress of 142.875. So if we solve this, I will get this d as 94.32 mm. So this d will be 94.32 mm. So I got this d, right? I got this small d. This small d should be how much? This small d should be 94.32 mm. 94.32 mm. So what about this thickness now? How much will be the thickness? This capital D minus small d, capital D minus small d, if I subtract this capital D, I mean if I subtract this small d from capital D, what I will get? I will get one thickness this side and one thickness this side. So basically I will get two thicknesses. If I subtract this small d from capital D, I will get one thickness this side, one thickness this side. I will get two thicknesses. So basically to calculate thickness, I will have to divide this capital D minus small d by 2. So if I do that, if I do this capital D minus small d by 2, I will get this as 101.6 minus 94.32 divided by 2. Therefore this T will be equal to 3.63 mm. So I get the T as 3.63 mm. Now from here the minimum T which is required is 3.63, and then here the light section itself has a thickness of 3.65. So there is no point in going for medium and heavy sections, right? There is no point in going for this. Even if I consider the light class of this pipe, it has a thickness of 3.65 mm, which is more than this thickness. So it will be easily able to withstand this load, and it will not exceed the stress of 142.875. So we shall recommend him this lighter section. And let me remind you, we are just not randomly suggesting him to use this. We have properly designed it. We have a proper approach through which we have found that the minimum thickness required is 3.63 in order to withstand this load of 160 kilonewton. So this is how we can use our knowledge of mechanics of solids to design these simple components.